this topic, so we're going to talk about it today. So the idea is we have some data that we can take a mean and a standard deviation of, and we want to be able to predict with a certain level of confidence that we can predict what the population mean is, because the population is usually a large number of data points which we don't know what they are, so we take this random sampling of the population, and the more samples we take, the better estimate of the population we have, but we still want to have some kind of idea of how accurate an estimate we can make. Is it, well, so what we're looking to do is we're looking to be able to make a statement that says I'm 90% certain, I'm 95% certain that the population mean is between two values. So this symbol here, mu, is what we call it's the population mean, not the sample mean, but the population mean. And that's what we're trying to, we're taking a sample to get the best estimate, but we can't test everybody, so we take a smaller subset that we actually measure and evaluate. So for example, we might say, the population mean, with 90% certainty, our population mean is between 74.3 and 80.2. So that's kind of the answer we would get to. Now, you might then also say, I'm 95% certain that the population mean is between 70.2 and 83.3. So the more certain you are about the population mean being within the two numbers, the wider it has to be. So if I said at 98% certain, then it'd be even wider limits. So I can narrow the limits, but I'm less certain about them. If I spread them out, I'm more certain. It's kind of like if you're playing a game and throwing. I'm pretty certain that if I had a hole this big to play golf, and I have a 4-foot putt, I'm pretty certain that I'm going to get it in the hole. But as I make the hole smaller, I'm less certain that I'm going to make it. Okay, so how do we get to that number? And what it really consists of is, so those numbers A and B are typically the mean, the sample mean, the numbers we average together and get a number, and then we add and subtract the same amount. And that amount will give a name. It's called the uncertainty, but it's a function of, so this plus or minus thing is a function of the standard deviation of the sample, because that kind of gives us an idea of how much the population is spread out, how inaccurate, or not inaccurate, but just how much spread you have. Okay, that's what the standard deviation. The number of samples. So this number is small. More samples you have, the smaller this plus or minus. The more certain you are about where the mean sits. And then the confidence level. So if you have a higher confidence level, you have D is bigger. If you have a smaller confidence, the higher percent confidence, the bigger D is. The lower the percent confidence, the smaller D is. And we'll see exactly what they're related to in a second. So here's so if the sample standard deviation goes up, D usually goes up. If the number of samples that you're testing goes up, the deviation goes down. And as the confidence level goes up, we have to open up the limits. So there's just general, if this is bigger, this is smaller, etc., that kind of stuff. So the first thing we're going to do is just go back and do a problem like we did for Chapter 12, Section 5, and also the end of the project, is we can answer this question, because those were all about population. When we did Section 12.5, we were talking about population means and population standard deviations. So if I said, given the population mean is 78 and the population standard deviation is 4.2, between what two values does 95% of the data occur? So that 95% here is percent or probability that you're going to be between two values, or the area underneath the curve. That's what this table represented. So there's the table. And as we've done with all these other previous problems, we we draw a picture to help us figure out what the heck they're being asked. So we're going to relate this to area when we look at the graph. So where did I do that? I guess I need to do it. I guess I left it so we would do it by hand here. So okay. So what we're going to do is we draw our picture. Okay. So where is my cursor? Hello, there you go. So we draw this axis, and we draw a little standard deviation thing like that. And at the mean, population mean, we write that down, 78. And what we're trying to do is figure out, what is this number? We'll call that A, and this number B, where 95% of the data, meaning 95% of the area, is underneath the curve. And what that means is if the total area under the curve is 1, or 100%, then the area under this curve is 0.025, and the area under this curve is 0.025, because added together you get 0.05, which added to 95 gives you 100. Okay, so what we're going to do is we're going to use the area. Instead of using the z-score to get the area, we're going to use the area to get the z-score. And then once we have the z-score, we can back out what A and B are. That's the plan. So in your assignment for the chapter problem, you were given the numbers and you calculated the area. In this case, we're given the area and we're going to calculate the numbers. So remember, this table goes from the mean out to here. So we know that let me just cross hatch it. So if we take this area that's all the way out to the end, the red area there, so I'll use red, that's equal to 0.5. Half the data is greater than the mean, half is less than the mean. This little sliver out here, the black area, is, well, this I shouldn't call it the black area. I guess let me move this red out of here for a second. Let's call it the blue area. So the little blue area is 0.025. And we'd have some blue over there, which would be 0.025. So the area that I'm going to use for using the table is this green area, which goes from the mean out to here. So that's the difference. If I take half the area, subtract the little blue area, that leaves me the green area, and that's what I'm going to use from the table. So A is equal to 0.5 minus 0.025, which is 0.475. So that's this area. And if I go the other direction, that's also the same area. And you add those together and you get 0.95. Okay, so now we go over to this table and we look under area for 0.475, and there, oops, disappeared on me. So it's right there, 0.475. So with this area, I get Z is equal to 1.96. Right? What did I say? 4.75, 1.96. That number right there. So now I can go with this z-score. I can then calculate the value. And remember how we did that? Z is equal to x minus x mean divided by s. And actually, I'm using sample notation here, but that's okay. So if I solve for, what I'm trying to do is find out what the corresponding x values are for this z-score. So I'll get x is x mean plus s, the standard deviation, times z. We used that before. So the mean was, in the problem, 78. Standard deviation was 4.2. The z-score was 1.96. So we get the corresponding value is that. So that'll give us the upper number, and if we subtract 4.2 times 1.96, we'll get the lower number. So 78 plus 4.2 times 1.96 is 86. 86.2. And if I do the same calculation but I subtract the standard deviation times the z-score, I get 78 minus 4.2 times 1.96, and I get 69.8. So those are the two numbers. So what I can say is that 95% of the data is between 69.8 and 86.2. So what I'm going to do with this confidence thing is I'm going to basically do the same kind of process. I'm going to say, instead of using percent data, I'm going to use percent certainty to define how far I go out. I'm still going to use the sample. Well, I'm not going to use the sample standard deviation. I'm going to use what's called the standard deviation of the sample means, and I'll explain that in a second. There'll be a special score here. It won't be a z-score. It'll be a t-score. But the basic procedure is the same as what we just done there, which we did in section 12.5. So first thing is, just like what makes sense, the best estimate of the middle point, the best estimate of the population mean is the sample mean, because I don't have anything else to base it on. So it's not like I have multiple sample means and take an average of those. I don't know what the population is. So the middle of that interval is going to be the sample standard deviation. However many samples I take, add the numbers together, divide by the normal way we calculate mean. Now, as the number of measurements increase in our sample, the sample mean is a better estimate of the population mean. That just makes sense. The more data you take, if you're randomly selecting data points or things to test, the more times you test it, you would think that would give you a better estimate of the sample mean. So that's going to help. But also, it's going to reduce the variability on where, how wide do I have to go to feel pretty confident that the interval I specify contains the population mean based on that. So by taking more data, I do two things. I get a better estimate of the sample mean, and I reduce the spread. So as the number of measurements increases, the sample mean is a better estimate of the population mean. I can also reduce the spread on either side. Okay. So it turns out, I don't know if they did this theoretically or if they did it just experimentally, but what we're going to do in this case is we're going to kind of do the same thing. This looks pretty much the same as what we just did with the z-score. We're going to have the middle of this estimation of the population mean centered around the sample mean, and we're going to add and subtract this d. And this is kind of a general concept, but I'll fine-tune it later. So what we're trying to say here is we have a 90% confidence. Now what does that mean? I don't know what that word means. Of means. What does that say? 90% of the data, 90% confidence. I don't know what that means. I can't. Yeah. So when we talk about 90% confidence, we're saying approximately 90% of the data lies between these two values, just like we said 95% of the data. It's not exactly that, but that's the general idea. Like I said, we'll elaborate on this later. But for right now, we'll say it's 90% of the data. So because of that, it's not surprising the technique is going to turn out to be pretty much the same. The key thing here is that the for each sample, you're going to have a sample standard deviation, but it turns out that the actual mean doesn't vary as much as does the actual data values. Let me show you the spreadsheet that we were looking at the other day. I think I do remember talking about this, but we'll redo it just so everybody's, just in case you weren't here. So let's see which one of these, demonstrating p-value. So these are different samples. These are randomly selected 13 data points out of my population of 1,000. And you can see, we were saying, I remember talking about this, about half of the data values are below the mean and about half are above the mean. The mean's about 50. So you can see the maximum is 53.5. The minimum is 46.2. But you got 1, 2, 3, 4, 5, 6 that are above the mean, and you got 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7 below the mean. And if you look at all these these are all just different samples, 13 samples, and all of them have about half of them are above the mean and half below the mean. So when you actually do the mean, the sample means, you can see they're not, they're not down to 46 point something, and they're not up to 50. Well, this one's 58. There's a lot less variation in the sample means than there is of the samples. And if you actually look at the variation, so if you looked at a histogram or you did a mean and the standard deviation of the sample means, you'd see there's a lot less variation in that. So we're much more confident about where the mean is than we are about where individual data points are. That's the point. And they came up with this relationship. So this, looking at the sample means, not the sample data, but the sample means, it turns out that we can use this procedure if this thing is normal, meaning it has a normal shape, like a normal distribution, a bell-shaped, if the number of data points is greater than 30, or if the population is normal. So the procedure we're going to go through works under these circumstances. In my case that I just demonstrated, the population is normal, so I could use any sample size, which I use 13. Why I chose 13, I think it was just where I ended up stopped dragging my thing. So Martha was getting her car, she has a leak in the car, in the trunk. We've taken it twice to the Honda dealer here, and it still leaked. So there's a guy in Roanoke called the Leak Doctor. And he lives in Radford, apparently, because that's where his phone number's from. But he goes to different car dealerships in Roanoke, and when they have a problem with a leak, for whatever reason, a seal or a crack, then he's an expert at fixing leaks. So she's been at the Leak Doctor for the car. She just said she finished, and they guarantee it for a year, so we'll see. So if you ever have a leak with your car, I'll have his number. I'll give you the leak. Well, let's see if he works or not, because if it works, we'll be happy. I mean, it's actually, I think the minimum charge is $250, so it's not peanuts. But if you got a leak in your trunk, you got to get it fixed at some point. Oh, you do? Yeah. Okay. So here's the procedure, and I think I've sent you the assignment, and somebody's already done it. So here's the procedure. This is the procedure for coming up with this range of numbers where you're certain percent confidence that the population mean lies between these two numbers. And that's why it's called estimations, because you're estimating where the population mean is based on sample tests. So the first thing you do is you calculate the sample mean like we normally do. Nothing new there. We calculate the sample standard deviation. We've done that many times. The third step is the first different thing, is we estimate the standard deviation of the sample means. So that's what I was saying, that this number the actual where the sample mean is doesn't vary as much as where the samples vary. And it turns out that so this is a sigma, which is a Greek symbol for S, as a small sigma. So it's kind of like I don't know, what does it look like? Anyway, it looks like that. And this is S bar. So this is the standard deviation of the means of the samples. And it turns out you can estimate it by taking the sample standard deviation and dividing by the square root of n. So if you have a certain variation in the data, you're going to have a narrower but proportionally spread in the sample means. But as you take more and as you have more and more samples in your sample that you're using, I had 13, but if say you had 25, this number is going to get smaller. Again, it makes sense. The more data points you have, the better estimate, not only of the mean, but of the variation in that quantity. So you just take the sample standard deviation divided by the square root of n. So that's not too hard. Now, in our previous example, we used z equals 1.96 to get 95% of the data. There's this thing called a t-score, and it's just almost like the z-score, except it's a function of the number of data points that you test. And I think I told you about that, the guy from Guinness doing that. So yeah. Yeah, so this t-score was originally developed by this guy at Guinness because, he realized he couldn't use z-scores because it was over predicting his confidence. And so I'm not sure how he came up with the table or the graph that plotted t-score versus area, but somebody did. And it turns out this t-score, the critical t-score, instead of being 1.96, it's based on this confidence level and the number of degrees of freedom. And so let me find that on the internet again. So you just look up the value in the table. Instead of having one table, the z-score is like having an infinite number of data points. Okay, so that's so this only looks at critical values, not at it's not worried about finding any area underneath the curve. It's just looking for the critical values that give you certain confidence levels. So so we look under critical t-score table. So there it is. And so you have two things to look up. You have, down at the bottom, you have confidence level, and you have number of degrees of freedom, which turns out to be just the number of data points minus 1 in this case. And you can see the numbers are, we had 1.96. You can see the confidence for 95% confidence is around 2. When we use z-score, we had a 95% of the data was plus or minus 1.96. So you can see here it is. With an infinite number of data points, you get the z-score. But when you have a finite number of data points, the multiplier pushes out, makes the spread wider. So the less data points you have, the wider you have to spread those limits out to be confident that you're including the sample, the population mean. This would be like 90% of the data. If we did that with the z-score, we'd find out 90% of the data is plus or minus 1.645 times the standard deviation. But as we reduce the number of data points, we have less certainty about that. Okay, so that's the table we're going to use. We'll keep that for right now, and we'll come back to it. And so using that, you can find the interval. That's what we're trying to figure out here. The mean, sample mean, plus or minus, instead of D, it's what we call capital E, which stands for the confidence, or it stands for the margin of error. So E is the margin of error. Mu is what we're trying to predict with a certain level of certainty. X bar is the mean of the sample. So the margin of error is just this critical t-score that we read from that table. This is the value we got in step 3, which is the standard deviation of the sample means, which is equal to the sample standard deviation divided by the square root of n. So we know all this, we've already got all that stuff. We just plug it into the equation, calculate it, add it and subtract to the mean, and we've got the answer. So let's do an example. So let's say we've taken 20 measurements of something. The mean is 52. That's the sample mean. So we've taken 20 readings, added them together, divided by 20. That gives you the sample mean. And the sample standard deviation is 2.6. What that means is, if we took plus or minus 2 times this, approximately 95% of the sample data would be between this minus 2 times that and this plus 2 times that. It's just kind of a rule of thumb. So the question is, what is the 90% confidence interval for the population mean? Should say mean. I don't see, let me scroll down, see if I wrote that down. Mean, yeah, okay. I did put it there. So, and that's what your homework problem is. I'm going to give you, I think actually I give you some data which you have to calculate the mean and the standard deviation from. And once you've gotten that, it's exactly like we're doing here. And I give you a video that shows you exactly what to do, so you shouldn't have any problem. Hold on just a second. It's just in case it's my wife. Nope, it's not. Okay, somebody from Blacksburg. Ignore that. Okay, so here's the calculation. We've already done the first 2 steps. Calculate the sample mean and the sample standard deviation. Third step is to calculate the standard deviation of the sample mean. So we just take the sample standard deviation divided by the square root of the number of data points. So that's our standard deviation of the sample means. Then we go to the table. So we go to the table, and we have 19 degrees of freedom because we have 20 data points, and we have 90% confidence. So here's 90% confidence. Here's 19 degrees of freedom. We look at the intersection of those two is right there, and you get 1.29. If you wanted 95% confidence, you'd use 2.093. If you wanted 99.99% confidence, you'd use 3.883. So it just depends on which confidence level you have. So we, based on the confidence interval and the confidence level and the number of degrees of freedom, we get 1.729. So we take the critical t-score times the standard deviation of the sample means, and you multiply these two numbers together, and it just turned out to be 1. I didn't plan it that way. So that's the margin of error. So the final step is to show the interval, and that all that is the sample mean minus the margin of error and the sample mean plus the margin of error. And the mean was 52, so it's 52 minus 1 and 52 plus 1. So that's our confidence interval. So what it's saying is we measured those 20 data points. I have a 90% confidence that the population mean is between these two values. Okay, now I'm going to tell you what confidence really means. It's not 90% of the data. So that's on the next page. I'm pretty sure if I can find my cursor. There we go. So what does this mean? Oh yeah, that's what I just said. 9 out of 10 times, 90% of the time, the population mean will be within the confidence interval determined using this method. So that's what that means. It doesn't mean 90% of the data. It just means if I use this procedure, the 90% of the time, I'm going to correctly bracket the population mean within those limits. So 90%, what does that mean? Well, 90% is pretty sure. I'd say I'm pretty sure that the population mean is between 51 and 53. I'm just making up these words. But, the lower the confidence, the less sure I am. So if I did the same thing, but I changed, say, to 90, what's my next one? So let's say 95%, 99% confidence interval, how would the calculations change? Well, you still have the same sample mean, you still have the same sample standard deviation, you still have the same standard deviation of the sample means because I still have the same data. The only thing that changes is this critical t-score. So instead of being 1.729, it's now 2.861. So my new margin of error for this confidence level, I have 1.66. So I add that and subtract that to the sample mean. So I take 52 and subtract 1.66, and 52 plus 1.66, which is a wider, it's going to be a wider area. And what that says, 99% confidence means that it says 99 times out of 100, if I follow that procedure, that the population mean will be between those two values. And you could go to 99.9% confidence interval, and you'd have, so it says, I'm really sure. 99% confidence is, 99 times 100. I'm pretty darn sure. If I said 99.9% confidence, I'd be really, really, really sure or something. Yeah, so let's see, I'm just going to look at it. So if I wanted to go to 99.9%, I'd multiply it by 3.883 instead of 99%, it was 2.6. Yeah. So your homework problem is basically like this. I'm going to give you the there's a paper that I sent with it. Gives you the data. So you can, from that data, you can calculate the sample mean, the sample standard deviation. You can count how many data points there are. I forget how many there are. And it's, I think, 95% confidence. So you're going to have to use the table, which you can get online, and just look it up. That'll give you the critical t-score, and you get some numbers. So that's all you'll need to know.
As long as you follow the video directly, then you should have done it right.
Right, yeah.
Okay.
Yeah, because I did the exact numbers. It's not like for the chapter problem I did different numbers, but I gave you the same, it was the same general concept. In this case, it's exactly the same.
Okay.
I think I looked at the scatter plot video where you have it marked opening at not the beginning. Is that where you want us to start? Or
Yeah, because I think I sent you the data for that, right?
yeah, I'm gonna open it real quick to see. It starts at
Yeah, that's,
10:30.
no, you should start at 0.
Okay.
You go back to the beginning. Yeah, that's,
Yeah,
I don't know why sometimes it opens. I think it's just the way I copy the address, but you should start right at the beginning. So let me just show you the two videos. I'm going to show you general what's in them, and you can, for the scatter plot and for the other one.
What was it? Because when I did the scatter plot, I was able to do it. And then when you sent the email saying that some people were having issues, I got really.
Oh, that was with the histogram.
Was that the part of the project?
Yeah, the Chapter 12 project. Some people I got an email saying,
Oh,
I'm having,
Chapter 12.
yeah, that was for the history.
Okay, I was kind of nervous because I did both of the homework assignments without any trouble, and I was kind of thinking I did something wrong.
Yeah, no, that was somebody said over in Rockbridge said they'd had some trouble doing the histogram. And so I went and looked at my video, and I thought, well, yeah, I guess maybe I could been a little bit better at explaining it, because I kind of went off on tangents there because I didn't. But when I did it, I realized that, and I was thinking, well, that shows them that what you can't do. So I left it in there, even though it probably could have been done a little more succinctly. Sometimes I do that just because I think it's worth seeing that people who do stuff don't do it perfectly. Sometimes you have to think a little bit and make decisions, so that's why sometimes I leave imperfections in there. Okay, so yeah, if you go to Chapter 12 Project Videos, you'll see that there's 2 new videos. There's the scatterplot assignment, which is 11 minutes and 50 seconds, so you definitely don't want to start at 10, or you're not going to get any. So it goes through and it shows you how to import the data and then create the scatter plot, which didn't take very much time apparently. So there's the data, and then it shows you how to create the scatter plot and to change the titles and stuff like that, and how to do the regression part of the calculation. So that's about 11 minutes long. And then there's what we just talked about today, which is the confidence interval. So that's about 12 minutes long. So you have to input the data yourself. And once you input it, you calculate the sample mean and the sample standard deviation. Then you calculate the standard deviation of the sample means. Then you look up the critical t-score. So here it is. There's the table. And then once you have the critical t-score, you can calculate. This was just to, oh yeah, this was something extra, but you can, when you watch it, I created a histogram just to show you how the data was kind of normally distributed. That was something I added. So if you do a histogram of the actual data points, you'll see that it's pretty normal. So that was to show you could use this procedure. Today, when I did today's stuff, I just gave you it, and we assumed that it was normal because we only had 20 data points. So for this procedure to work, these measurements have to be normally distributed. So in this case, I just proved that. And once I did that, then you can calculate the margin of error, and then you can add and subtract that, and it gives you the interval. So then, and then there was just just one last comment of what this all means. So that's the assignment for confidence interval. And it's, like I said, the data is exactly the data that's in the project. So the only thing I paused the recording while I entered the data, so you'll have to do that yourself. You should be able to do it. Okay, so that's the assignment. Before we move on to the next topic, which is the last topic in Chapter 12, I wanted to show you so what I did was I basically created these confidence intervals for each sample set. So I'm doing the same procedure that we've just gone through. I'm going to do it for each one of these samples. We only did it for one sample. So the first thing you do is you calculate the sample mean, sample standard deviation, the standard deviation of the sample mean. So this number is that number divided by the square root of 13. Then you add, it says plus or minus 2 standard deviations, but if I click on that cell, it's really plus 2.179, and that's that critical t-score. So I take the critical t-score and multiply by that number, which is the standard deviation of the sample means. So I'm adding the margin of error and I'm subtracting the margin of error. And so this is my confidence interval, and it's 95% confidence. If we go back to that table, you'll see that where's my table? So there's 13 data points, so there's 12 degrees of freedom, 95% confidence interval. It's that number right there, 2.179. So that's where I got the 2.179 in my calculations. So you can see it's 95% confidence down here. So so I did that for each sample, and then I had this. What I did is I said, if this number is greater than 50 or this number is less than 50, then it's outside of the interval. So when you get a 0, it means it's within the interval. So this one's within the interval. This one's within the interval. because 50 is between these two numbers. And in this case, I know what the population mean is, so I'm just demonstrating. Normally you wouldn't know what the population mean, but it's just showing if you have a population with a certain mean and you use this procedure on various random samples, how often does it work? So if I go to the right, you'll see at some point I'll get a 1. You might not believe it, but it does happen here sometime. There we go. Okay. So this particular, where's 1? Right here. This was my upper limit. This is my lower limit. So this is above 50. So my prediction of taking this data, this particular sample, with this mean and this standard deviation, it turned out that I would have estimated that this population mean was within this, and it's not, because I know what the population is. So that's a 1. And that happens every once in a while. Here's another case right here. So again, it's on the upper side. So I put a 1. These are between. And if you add those numbers up and then subtract this number calculation here is the percent of the time that it works. So 0 works, 1 doesn't work. If you look at, I had like 70 some samples, you see that 96% of the time the procedure did work, and that's what the confidence interval means. And I did this not in this sheet, but I think I have it on another one where it'll do a whole bunch of samples again, and let's see here. Just gotta find it. Yeah, I'm not sure if I can't remember where I put it. Anyway, you can have it so it'll pick another 70 samples, and it won't be 76% of the time, 96% of the time, all the time. Sometimes it's 94, and sometimes it's 92 point something. But I did it over like 20 different samples of 70, so it was a huge amount of stuff, and it came out to be 74.8% of the time it worked. So that's what confidence interval means, and it was kind of cool that I could demonstrate it, at least to myself, that it does work. Okay, so and the last topic we're going to do here is called hypothesis testing. And then we're going to move on to chapter 13, which will be the last chapter. So what we're going to do in this case is we'll answer this question: is a measured difference in a property due to random chance, or is the difference what we call statistically significant? By looking back at that measurements that I just demonstrated, the mean isn't always equal to 50. Sometimes it's higher, sometimes it's lower. And so, if the change measured is small enough, it may be due to something really being different. It may just be due to the random nature of sampling and the distribution of data in a normal fashion. And when they do hypothesis testing, the hypothesis that they compare it against is what's called the null hypothesis. And so you always assume that doing something causes no change. So there's the null hypothesis, which says there's no change, and then there's the alternative hypothesis, which there is change. So you never say, I'm going to hypothesize that I'm going to increase the thing by 10%. What you do is you'd say, I'm going to hypothesize that there's no change, and then I'm going to prove that I was wrong, that there is a change. Okay, so the alternative hypothesis is there is a change, and the reason it's called a null hypothesis is null means no, so there's no change. Now the question is, there's three ways you can look at it. You can say the change is an increase, you can say the change is a decrease, or you can say the change is either an increase or decrease, which we're not going to get into the subtleties of that. We're just going to demonstrate one particular case just to kind of give you an idea of how people do this when they run experiments and they look for differences. Now, when you actually complete your test, you don't say, I'm going to accept the null hypothesis. There's two results. One is to fail to reject the null hypothesis, which is equivalent to accepting the null hypothesis. So if there's no change, we don't say we accept the null hypothesis. We say we fail to reject the null hypothesis. So it's a double negative. Seems like a crazy thing to do, right? But there is a reason behind doing that. Just because we're never certain, because we're doing this to a certain confidence. And so we're never 100% sure. So I think that's why they do this, fail to reject the null hypothesis. If there's no change, we'll say we fail to reject the null hypothesis. Now, if there is a change, so we're usually hoping for a change, or it's kind of like waiting for something not to happen. So not that you try to make it happen, that's cheating, okay? But usually you wouldn't say, I think I'll design a drug that doesn't do me any good, and I'll subject all these people to this drug that doesn't do any good. You're usually designing something to try to make something happen. So typically you want something to happen, and you want to know if that thing happening is real or just chance. Okay, so the other option is reject the null hypothesis, which is the same as accepting the alternative hypothesis. So those are the two possible answers. So we're usually hoping for a change. Those are the two results we can have. Okay. And typically in these kinds of experiments, now if we're doing a scatter plot, we're usually changing one variable, but we're not just changing it to one level. We're not saying let's have a placebo and let's have 10 milligrams of this drug. When we do a scatter plot, we're probably doing 0 and 5 and 10 and 20, and that's usually when something's not as planned. Like if you're plotting temperature versus time, you're not controlling the temperature of the earth or something like that. You're measuring it, you're observing it. Here we're controlling things, and a lot of times you say, okay, we'll have the placebo, the control, and we'll have the experiment. And we want to know whether that difference in the drug makes a difference in the response to whatever you're designing the drug for. So we change the independent variable, the drug dose, and we're going to measure the independent variable, which would be things like survival or something like that. So we're going to use this as an example. We're going to do a chemical process. So let's say that you've been running this chemical process for a year, and the data, a huge amount of data, says that the yield for the old process is 45%. If you make paper, you bring trees in and you get fiber out, and there's yield. So you can think about paper making. You don't use every last part of a tree. You get rid of the bark, and even the stuff that holds the fibers together, you get rid of the lignin. And so that's kind of you don't always get everything out that you hope to get out. It's not perfect. Okay, so now what we do is we make a modification to the process. So let's say we increase how long the stuff is in there cooking away or reacting, and we repeat the new process 20 times. Because if you just do it one time, you don't really know. You don't really know if that's just due to random luck. That's why if you see something good, you always repeat it. Even bad, you should repeat it, because it may just be a anecdotal result. It's not representative of what happens all the time. Okay, so we repeat the new process 20 times, so that's the number of data points. And the new yield is 52.2% when you average them together with a standard deviation of 4.2%. So the question is this increase in yield real or not? Or is it statistically significant? Or could this increase in yield just happen because of variations in the original process, and we could every once in a while we could get that after measuring 20 samples. 20 of the samples here might average 50.2%. Who knows? So is this measured increase statistically significant? And all you need is the old standard, the new mean, and the new standard deviation, and the number of samples. And you also need to think about confidence. How confident am I that the difference is real or not? And what we're going to do is we're going to assume that the standard deviation of the new process is not necessarily equal to the old process, or we don't know what it is. We don't know what the old standard deviation is. All we know is what the standard deviation is from our 20 measurements that we just did. We do know the previous mean, but we don't know what the previous standard deviation is, or they're not the same. So if we did, we might not have to use t-score. We could use z-score. But like I said, I'm just trying to give you a feel for the general kind of idea process you would do. So in our case, the null hypothesis would be that there is no change. Remember, null hypothesis means no change. We're hoping there is a change, so hopefully we can reject the null hypothesis and say there is a change. Most likely somebody's done some kind of lab experiments to show that this should improve, and you want to check it out on a real full-scale process. So you don't just randomly do stuff. There's some process, whether you do it theoretically or do it experimentally, you've probably done some background work. If you're doing drugs, you've done tests on rats or something like that at least with rats it did something. So now you're going to try it on real people. Okay, so the null hypothesis would be that there is no change in the yield, and the change we are seeing is due to the random nature of the process. The alternative hypothesis is that there is a change, and it's not just random, it's actually due to the change that we made. So what we're doing here is we've got the old process, which had some mean, 45, and even the old process had some variation around that value, the standard deviation. And then you've got the new process, which also has a mean, and there's a distribution around that. And even though there's an overlap between the two results, doesn't mean that they can't be statistically significant. Obviously, the further away the means are, the more likely it is that there's statistically significant difference. The other thing that affects it is how spread out these. If the data went like this and this data went like that, it would be easier to conclude that there's a difference. But a lot of times there is still some overlap. So you could have some of the old process give higher yield than the new process, but on average the difference is there, possibly. Okay. So just the point here is just because some of the old may be better than the new doesn't mean that there can't still be a significant difference between the two. So the yield using the old process will sometimes be higher than the yield using the new process, even if the means are different, just because of the standard deviation of the measurements. So this is our null hypothesis, that the population of the new process is equal to the population mean of the old process. Our alternative in this case is that the population mean for the new process is greater than the population mean for the old process. Now we don't have this value. We can use confidence interval to kind of figure out where we think it's going to be, but we can't know it exactly. Now, we could say, is it less? Well, it's probably never. It's not going to be less than based on the data that we already have, because if the sample mean in the new process is greater than the old process, it's not going to be the other way. So we can kind of guess that it has to be at least greater than, if there's any possibility. So there's 3 ways of doing this, and they all give you the same answer, whether relative to rejecting the null hypothesis or failing to reject the null hypothesis. The first one is the least likely people use, but it goes along with what we just talked about, estimation. So what we do is we take the new data and do exactly the same procedure that we did a few minutes ago and define the confidence interval. And if the old population mean is in one of these tails of the confidence interval, meaning it's outside of the confidence interval that we specify, then we reject the null hypothesis, and there is a change. If this new mean is within the confidence, if this old mean is within the confidence interval, then we fail to reject the null hypothesis. So the procedure is just, the only difference between what we just did and what we're doing now is when we get the confidence interval, we're going to see whether the old mean is inside or outside that confidence interval. So it says if mu old is outside the confidence interval for the new process, the interval for the population mean for the new process, then we reject the null hypothesis. And therefore the new mean is statistically significant difference. It's big enough. The difference is big enough. So we're going to use the data that I've already presented. 45%, that's going to be this. X bar new is going to be 50.2. We can use the new standard deviation and the number of data points to calculate the margin of error, and we can figure out the confidence interval. So we'll probably get that far, and then we'll talk about the other 2 methods next time. So first step, this is not exactly the same as the steps for confidence interval, but it's pretty much the same. So in this case, I just write down what the old population mean was, 45% yield. The new sample mean was 50.2%. The new sample standard deviation is 4.2%. So then the step after this is to calculate the standard deviation of the sample means. So we're just going to take this number divided by the square root of 20. Okay, so that's the next step, just like we did before. So the standard deviation of the sample means of the new data is the new sample standard deviation divided by the square root of the number of data points, which is 20. So I get 0.94. We just looked that up a minute ago. From the table, this is based on 19 degrees of freedom and 95% confidence. So we're going to use 95% confidence interval. Find that in the table. You take this number times that number. That gives you the margin of error for your confidence interval. So we use this and that to get that. And now we're going to add and subtract this number from our sample mean that we tested. And then we're going to see whether those 2 numbers, if this number is inside those 2. Okay, so here's our margin of error. We add 1.62 and we subtract 1.62. So our 95% confidence interval for the new sample or new population mean is from 48.6 to 51.8. Well, the old mean is 45, which is outside of that. So because the old sample or the old population mean is outside of the confidence interval for the new population mean, what we're going to do is we're going to reject the null hypothesis. We're accepting the alternative hypothesis, which was there is a change. So we would say there's a statistically significant change in the yield due to whatever process change we made. So since this 45 is not in the confidence interval, we reject the null hypothesis. Actually, we have more time than I thought we had, so we're going to continue on here. Okay. Hence, the measured change is statistically significant. In the homework problem, you have to do it all three ways. So I'm not going to. Okay, so the other two methods, this is an example of a one-sided test because our alternative hypothesis was that the new population mean is greater than the old population mean. Another option would just been that the new population mean is different than the old population mean. It could be greater than or it could be less than, and you have to do things differently under those circumstances, but we're not going to worry about that in our case. If you ever take a statistics class. Another one could be that the new mean is less than the old mean, but that's highly unlikely in our case because our measured, we're trying to improve it. We probably did some background stuff, so most likely we would use this original alternative hypothesis because we've done some preliminary work which indicates that it would help. We just don't know how much. Okay, so that's what that's just saying that this one really doesn't make any sense for this point. Okay, so these are the other two methods. One's called the critical region method and one's called the p-value method. And this is the one that most people use these days. These are very similar. There's only like one step that's different between these two. So once I've done this one's going to be, and the reason this one is last is it's harder to find a value unless you have a software to do it than this one. So the advantage of the p-value method is it gives you a better idea of how big a change you have, how statistically significant it is. You know, in the previous one, I just said it was outside of the interval, and I said, yeah, statistically significant, but I didn't really say it's really statistically significant or it's sort of statistically significant. So the advantage of the last method is it does give you a better feel for how likely the experimental results are really truly due to a process change. So the way this changes is now instead of having the distribution around the new sample mean, we do the distribution around the old sample mean. And we assume that the standard deviation of the old process is equal to the standard deviation in the new process. So it's kind of the same kind of relative thing. I have my new sample mean out here, and if it's in this area, which represents 5% of the area underneath the curve, then I would say this is statistically significant. There's only a 5% chance or less that the measured difference is due to random sampling rather than due to the actual process having this occur. So what we're going to do is we're going to find a critical t-score here. Before we used it to set the critical t-score to set the confidence interval. Here we use the critical t-score to determine whether our actual t-score based on the data is greater than or less than the critical value. If it's greater than the critical value, then it's statistically significant and it's in this region. If the t-score is less than the critical value, then it's in this area and it's not statistically significant. So you won't see a whole lot of difference between all three methods. It turns out that a 90% confidence interval is equivalent to using this is called the significance level. And most of the time, significance level is either 0.5, 0.05, or 0.01. And so that we're going to use this in the table to figure out what the critical value is. And if you look at the table, you'll see that we've been using the bottom scale, but if you look at this, here's confidence level, and we use 90% confidence. That's where we got the 1.792 from. But if we go up here, this is alpha. So an alpha of 0.05 is equivalent to a confidence of 90%. So we're going to use the same value, the same critical t-score in both of these methods. Okay, so here's the method. I get part of the way. So I have the same population, initial population mean. This is our sample mean, sample standard deviation. Still 20 samples, 19 degrees of freedom. Instead of 90% confidence, we're using alpha equal to 0.05. The critical t-score is a function of instead of n and alpha, not n and confidence percent. But we get the same number because these methods are equivalent to each other. So it's just looking at the bottom instead of the top instead of the bottom of the table, but you get the same number. So that's your critical t-score. You calculate the standard deviation of the sample means, which is the same number, sample standard deviation divided by the square root of n. And then this is the step that's different. Instead of calculating a margin of error, you calculate a t-score based on your sample mean and your population mean and the standard deviation of the sample means. So this is my sample t-score, 5.5. My critical t-score is 1.729. So since this is greater than that, okay, so since this t-score is greater than the critical t-score, it puts us out in that tail. And so based on that result, we can make this conclusion. So because this happens, we reject the null hypothesis, which is what we did using the confidence interval method. And the more t is greater than t critical, the bigger this number is, the more sure we are that our decision to reject the null hypothesis is correct. So we're pretty darn sure, because a t-score of 5.5 is almost impossible to get through chance. So it does give you some idea of how sure you are. If you ended up with a t-score of 2 versus a critical t-score of 1.729, you'd be less sure. If you got a t less than 1.729, then you would fail to reject the null hypothesis. There's still a large enough chance that the difference is due to random sampling. So that's the critical t method. The only thing we had to do differently was we just had to look at same column, we just had to use a different number to get us in the same place. We still calculated the critical t-score. We still calculated that. This was the only new thing. We calculated t-score instead of a confidence interval. And then we compared the two and made our decision based on that. What we'll find out next time is that the p-scores is the probability that we get this number based totally on chance. And there we compare the p-value versus this number. And if the p-value is lower than the significance level, then we reject the null hypothesis. So the only difference is, instead of calculating t critical, we take this number and we calculate the p-value, which is not easy to do. Not as easy to do as going the other way around. So we'll do that, and then we'll be done with it. So I'm not going to assign this assignment yet. I'll do that next time, which is the last assignment, which is hypothesis testing. So hopefully, like I said, the whole purpose is just to get a kind of a feel for how people do scientific studies and what factors into making decisions about whether it's statistically significant or not. Okay. And you have a question about